Hello again. Welcome to our lecture on the law of cosines. Last time we saw the law of sines, and it aided us in solving triangles. Given certain pieces of a triangle, maybe some sides, maybe some angles, we were able to construct or determine the other sides and angles of those triangles. Today, the law of cosines will permit us to also solve triangles, in particular, two outstanding cases that we didn't look at last time. One will be the case of side, side, side. Given three sides of a triangle, can you find the three angles? And the other case would be side, angle, side. You're given the two sides and the included angle. And again, the law of sines did not permit us to handle that case. We'll also see a few really practical applications of this law of cosines. In calculus courses, my feeling is that the law of cosines tends to occur more than the law of sines. It tends to be a more powerful tool in applications, but you should really know how to use both of them. And I think they're they're very pretty theorems to begin with and not too difficult to memorize. So what does the law of cosines say? We'll start again with our favorite little triangle, ABC. And the sides opposite the angles labeled ABC are labeled with lowercase letters ABC. So the side opposite angle A is lowercase a, etc. Here's what the law of cosines says. It's really nice. The law of cosines says that A squared equals B squared plus C squared minus 2BC cosine A. Let's look at that picture again and savor this formula. It says that A squared, in other words, the length of the side A equals B squared plus C squared, the other two sides, minus 2 times the product of BC, those same two sides, times the cosine of the opposite angle, the cosine of A. And of course, you could use this theorem with the letters rotated. You could express it as B squared equals A squared plus C squared, blah, 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 etc. There are three, in reality, there are three law of cosines depending on which side and angles you select. Okay. Now look at this theorem for a moment. Look at this formula. Do you recognize any of these creatures in this formula? Or let me say it a different way. What if the angle at A were a right angle? What if you had a right triangle here? What is this theorem saying? Well, if the angle at A is 90 degrees, a right angle, the cosine is 0. And the formula collapses to, hey, the Pythagorean theorem, A squared equals B squared plus C squared. So in many ways, this is a generalization of the Pythagorean theorem. It's the Pythagorean theorem applied to triangles that aren't right triangles. In fact, the proof of this theorem and the proof, again, of the law of sines both involve some kind of triangle manipulation based on the Pythagorean theorem. Okay, now let's stare at this formula again. What does it tell you about solving a triangle? Well, if you know little b and little c, if you know the length of two sides and you know the included angle A, then you could apply the law of cosines and find the side opposite that angle A. That's how the theorem goes. Little a squared equals b squared plus c squared minus 2bc cosine A. So given two sides and the included angle, you can solve the triangle, or at least you can find this side and then you could repeat it and find all the other angles. Okay, but let's write the law of cosines a different way. Solve for cosine A in the original equation. Well, first you'd have 2bc cosine A equals b squared plus c squared minus a squared. In other words, I moved the terms around a little bit. And then divide by 2bc, and you have a new form of the law of cosines. Here it goes. Cosine A, cosine of an angle A, equals b squared plus c squared minus a squared divided by 2bc. Now, what does that tell me? That tells me the following. If I know the sides of a triangle, A, B, and C, I can plug them into that equation and discover the cosine of the angle A. In other words, I can get an angle knowing the three sides. That's what we'll do in this next example. So here's the setup. We're given three sides of a triangle, and we're supposed to find the three angles. So this is like a side, side, side problem. Okay, here's our triangle. We'll label it as usual, ABC, and the sides will be 8 opposite angle A, 19 opposite angle B, and 14 opposite angle C. The goal is to find the three missing angles. Angle at A, angle at B, angle at C. Okay, here we go. I suggest that you start with the side that is longest, side B. And in a minute I'll explain why in more detail. So let's use the law of cosines, but in the form where b squared equals a squared plus c squared minus 2ac cosine b. So that's the law of cosines. We know that we can solve this now for cosine b equals a squared plus c squared minus b squared, all divided by 2ac. That's the other form of the law of cosines. And we know everybody on the right-hand side here, don't we? We know a, b, and c. We know the three sides of this triangle. So it's 8 squared plus 14 squared minus 19 squared, all divided by 2ac, 2 times 8 times 14. So it's kind of an unpleasant quotient there. You can add these on your calculator, and you can then divide, and you'll get approximately minus 0.45089. That's an approximation of cosine B. Okay, let's pause here for a moment. This cosine is negative, isn't it? Cosine B is a negative number. What does that tell you about the angle B? If your cosine is negative, where are you? What quadrant are you in for negative cosine? That's right, quadrant 2. So this angle is actually obtuse. It's bigger than 90 degrees, and of course, less than 180. So by using our calculator, we can do the inverse cosine function and discover that B is approximately 116.80, and notice indeed it's an obtuse angle because the cosine was negative there. So this last step, I had to use the inverse cosine button on my calculator. I knew what cosine B was, and I knew it was going to be obtuse, the angle B, and the inverse cosine button gave me that approximation. Okay, what do we do now? We know three sides and one angle now. We're missing two more angles. And you have a couple of choices here. You could again apply the law of cosines to the other angle, to another one of the angles, or you could use the law of sines. And why don't we do the law of sines, just because I think it's a little bit simpler. So now let's find, we know what angle B is, let's find angle A. So sine A over A equals sine B over B. Remember, that's the law of sines from the previous lecture. That means that sine A equals A times sine B divided by B. Plug in the numbers, 8 times sine of 116.80 degrees divided by 19. Remember, side A was 8 and side B was 19, and we get approximately 0.37583. And then do the inverse sine function. A comes out to be approximately 22.08 degrees. I know A is going to be an acute angle here because already B was obtuse, and the full triangle can't have two obtuse angles, can it? So the other two are going to be acute. So A comes out to be 22.08, and then knowing two angles, subtract 180, and we have 180 minus A minus B, and that turns out to be about 41.12 degrees. Whew. So what did we do? Started with three sides. The law of cosines gave us one of the angles, And then we figured out the other two using the law of sines or, again, the law of cosines. Again, I recommended that you find the largest angle first. Here's the reason. If the largest angle is obtuse, then you can be sure that the other two are acute angles. And of course, if the largest one is acute, then of course everybody's going to be an acute angle. Good. Remember, from our trig knowledge a long time ago, if cosine is positive, the angle's between 0 and 90 degrees. It's an acute angle. But if cosine is negative, you're over there in the second quadrant, and the angle is between 90 and 180 degrees. It'll be an obtuse angle, as in the example we just did. All right, let's move on to another example, the other kind of example that for which the law of cosines is a powerful tool, and that's the situation of side angle side. So here's a little problem to look at. As usual, triangle ABC, let's assume the angle at A is 25 degrees, and the two sides next to A are 9 meters and 12 meters. You might have noticed I don't make a big deal about units here. Sometimes we use feet, sometimes we use meters, sometimes I forget to use units at all. That's not too important for the mathematics, but rather the final answer, of course, should be expressed in the correct units. So we have two sides and the included angle. How can we get the rest of this triangle? Well, the first thing we could figure out is the opposite side, the side opposite angle A, and this is a perfect setup for the law of cosines. Here it goes. The law of cosines says that A squared, that missing side, is B squared plus C squared minus 2BC cosine A. That's precisely the law of cosines applied to our situation. Plug in the numbers. 9 squared plus 12 squared minus 2 times 9 times 12 cosine of 25 degrees. A was given to be 25 degrees, and you end up with about 29.2375. That's A squared. So take the square root, and it's about 5.4072. Okay, we now know all three sides of our triangle, don't we? So we're kind of back in the other case. We could find, say, one of the other angles now. Sine B over B equals sine A over A. Here I'm using the law of sines. That gives sine B equals little b times sine A over A. Plug in these characters. 9 times sine 25 divided by 5.4072 yields sine B approximately 0.7034. Okay. Now you might remember from the previous lecture that when the sine of an angle equals, say, 0.7034, you kind of get nervous a little bit because there are two possible angles having that sign, just like there was in the previous lecture. This is kind of that complicated case. But don't worry, here it's much easier. Here I know B has to be acute, because back in the picture, the longest side was C equals 12. So the angle at C is the largest angle in this triangle. So B is definitely an acute angle. Good. So we can take the angle for B, and it turns out to be, in this situation, about 44.7 degrees. I obtained that by taking the inverse sine of 0.7034, and that yielded 44.7, and I didn't have to worry about the other solution to that equation, which turns out to be, by the way, 135.3 degrees, but that can't happen in this triangle. So B must be acute. We now know B, we know A, and hence the angle C is the subtraction 180 minus 44.7 minus 25. C is 110.3 degrees. Whew. Took a lot of work to solve that triangle. But I think you see now the power of the law of cosines. We've done two examples, side, 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 or side, angle, side. We've basically covered all the possibilities now of, given three pieces of a triangle, find the other three pieces, except for the obvious case, What is that obvious case where you can't solve it? Right. Angle, 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 because the triangles could be different sizes, like similar triangles. Now, where do all these laws come from? Law of sines, law of cosines. History's a bit obscure here, but it seems that Persian mathematicians in the Middle Ages knew about these laws and were the first to really work with them. Nasir al-Din al-Tusi in the 13th century seems to have developed the law of sines, and al-Kashi in the 15th century seemed to be the first one to use the law of cosines. That said, historians believe that Euclid probably knew these ideas about solving triangles, etc. But he couldn't have had the law of sines or cosines because trigonometry hadn't been invented yet. But I think Euclid probably knew what was going on. If he had had trig there in front of him, I think he would have been able to figure these out. All right, let's do an application to baseball. In fact, to softball. I love this application because the Florida Gators, my university, has a great women's softball team. They always seem to do very well in the Southeast Conference and nationally. And I've been to a lot of games there and learned a lot about the dimensions of a softball field. And it turns out in a women's softball field, the pitcher's mound is 43 feet away from home plate, and the bases are 60 feet apart. So here I've drawn a softball field, and notice that it's a square, 60 feet on a side, and the pitcher's mound's there in the middle, and it's 43 feet away from home plate. So I'm going to label the pitcher's mound P, home plate H, and first base F. And the distance from first base to home plate is, of course, 60 feet. So here are the questions I'm going to ask about softball fields. How far is it from home plate to second base? How far is it across that entire diagonal of this square? And the second question is, how far is it from the pitcher's mound to first base? Suppose you had to throw the ball from the pitcher's mound to first base. How far is it? The answer is slightly surprising. So let's do the first question. This will require the Pythagorean theorem, because if you look at the picture, to find d squared, where d is the distance from the home plate to second base, that is 60 squared plus 60 squared, all square rooted. You can see a right triangle with sides 60 by 60 and the right angle at F. And then the hypotenuse would be the line from H going through P and intersecting second base. So again, using the Pythagorean theorem, we have side squared plus side squared, 60 squared plus 60 squared equals hypotenuse squared. So that's 60 squared plus 60 squared turns out to be 7,200, and that's the square of the distance from home plate to second base. Taking the square root of this number, it turns out to be about 84.8528 feet. Well, that's kind of interesting. Remember, the home plate to the pitcher's mound was 43 feet. If the pitcher's mound were halfway to home plate, halfway between second base and home plate, then that full distance would be 86 feet, wouldn't it, from home plate to second base? But it's not. The distance from home plate to second base is 84.8528 feet. The bottom line is the pitcher's mound, being 43 feet from home plate, is not halfway between home plate and second base. Now, it's not off by much, about a foot and a little bit more, but that was kind of curious. It's not in dead center of that square. It's not in the middle of the square, is it? All right, let's do the second question. And that was, how far is it from the pitcher's mound to first base? So let's label that distance H from the pitcher's mound to first base. It's the side opposite the angle labeled H in the triangle HPF. So who are the characters in this triangle? H to P, that side is 43. That's the distance from home plate to the pitcher's mound. H to F is 60 feet. That will label P because it's opposite vertex P. Now, what about the angle at H in the triangle? Well, the line joining H and P bisects that 90-degree angle at home plate, doesn't it? So the angle at H is 45 degrees. So we can use the law of cosines. Isn't this neat? We know little f is 43. We know that side. We know the other side is 60. And the included angle is 45 degrees. So the law of cosines is perfect here. Here we go. H squared, that's what we're trying to find, is f squared plus p squared minus 2fp cosine h. So it's 43 squared because f is the distance from the home plate to the pitcher's mound, plus 60 squared, that's the distance from home plate to first base, minus 2 times 43 times 60, I'm just doing the law of cosines, times cosine of the included angle, and that angle was 45 degrees. If you do the arithmetic on that, it's about 1,800.33. That is h squared. Take the square root of that number, and you get about 42.43 feet. Curious answer. Not quite as far as from the pitcher's mound to home plate. Okay. Let's do another application of this law of cosines. This would be useful if you wanted to measure something, and if you wanted to measure a certain distance between 2 points, but you weren't able to do a string joining the 2 points. There might be water in between. In fact, that's how we'll word the problem. You've got this marsh, and here's a picture of a marsh, and you're standing at point A, and you walk to point B, and suppose it takes you, it's 380 meters to point B. So you start at point A, and you walk to point B, and then you turn 80 degrees and walk to point C. And the distance from A to C will turn out to be the length of that marsh. So let me say it a different way. Here's this marsh, and you want to find how long it is, how far it is from A to C across the marsh. And of course, I don't want to swim it. So what do? I start at A, I walk 380 meters, make a turn of 80 degrees, walk another distance, 240 meters, and then I end up at point C. Will I be able to find the length of the marsh? Doing this little trick of starting at one point, walking a certain distance, turning an angle, walking another distance, looking back and say, yeah, I've crossed the marsh without having to swim, and I can figure out how big the marsh is, how long it is from A to C. Well, this is clearly a law of cosines problem. Here we go. We've got two sides, don't we? We have the sides 380 and 240, but we don't quite have the angle at B in our triangle ABC. What we do have is the exterior angle of 80 degrees. So that means the other angle is going to be 100 degrees. 180 minus 80 is 100. So now I know the included angle. It's 100 degrees. And the law of cosines will give us the final answer. B squared equals A squared plus C squared minus 2AC cosine B. That's a statement of the law of cosines. And plug in the characters, 240 squared plus 380 squared minus 2 times those numbers, 240 times 380, times the cosine of the included angle, which was 100 degrees. Punch that on our calculator, we get a big number, 233,673.4. Wow. But it's the square root we want, and the square root's about 483.4 meters. So I figured out how far it is across this swamp without having to get my clothes dirty, and by this little trick of walking around it and making sure I measure the angle that I turn halfway during my walk. Okay, good. That was, I thought, another interesting application of the law of cosines. You be the teacher for a moment. Can you solve the following triangle? Suppose I say, here's a triangle. Try to solve it with the law of cosines. And the sides will be 10, 16, and 4. Let's try to use the law of cosines to find one of the angles. We're given 3 sides. 16, 4, and 10. 3 sides. Here we go. Well, a squared equals b squared plus c squared minus 2bc cosine a. And why don't I label a 16, b 4, and c 10? Let's plug them in. Cosine a equals b squared plus c squared minus a squared divided by 2bc. That's that alternate form of the law of cosines. Plugging in the characters, 4 squared plus 10 squared minus 16 squared, all divided by 2 times 4 times 10. That turns out to be about minus 140 over 80, or minus 1.75. Uh-oh, what do you say to yourself now? The cosine of A is about minus 1.75. It's exactly minus 1.75. What's A? What's the angle at A, given that its cosine is minus 1.75? Right. There is no such angle, is there? Cosine is always sandwiched between minus 1 and 1. That was the original property of cosines. This number is too far below minus 1. It's too negative. So there is no such triangle because this angle can't exist. Now look back at the 3 sides. You might have noticed something from your geometry classes. In these dimensions, b plus c is 14, which is less than 16. That can never happen in a triangle, can it? The sum of 2 sides always has to be greater than the 3rd side. Now there's an area formula associated with the law of cosines. Associated meaning it's proven by using the law of cosines. Let me just mention this formula briefly. It's often called Heron's area formula after Heron of Alexandria, who developed it in the 1st century AD. It says that the area of a triangle is the square root of the following quantity: s times s minus a, s minus b, s minus c. Who are these characters? Well, a, b, and c are the sides of the triangle, and s is what's called the semi-perimeter. It's the perimeter, a plus b plus c, divided by 2. Let's try this for the 3, 4, 5 right triangle that we've used previously in our trig studies. Let's calculate the area of the 3, 4, 5 right triangle 2 ways. It's pretty easy to do this triangle, but I just want to illustrate how the formula works. So one way to do the 3, 4, 5 right triangle is 1/2 base times height. So it's 1/2 3 times 4, 1/2 12, or 6. That's pretty simple. Let's do the other way. Let's do Heron's formula just to get a feel for how it works. Well, you have to calculate this semi-perimeter. So that's a plus b plus c over 2. 3 plus 4 plus 5 over 2, that equals 6. So the perimeter is 12, and half the perimeter is 6. And now plug in all the characters. Square root of s times s minus a, s minus b, s minus c, which gives the square root of 6 times 6 minus 3, 6 minus 4, 6 minus 5. If you simplify that, you get 6 times 3 times 2 times 1, square root of 36, or 6. Whew, the same answer. Isn't math lovely? You do a problem 2 ways, you come up with the same answer. Okay. Remember a few minutes ago, we saw a, quote, triangle with sides 10, 16, and 4. What do you think happens if you try to find the area of that triangle? Heron's formula is amazing that you can find the area of a triangle knowing just the 3 sides. Well, I'll leave it to you to show that if you try to do Heron's formula on this non-existent triangle, you'll end up with a square root of a negative number. And that's, again, impossible. So Heron's formula would fail because no such triangle exists. Okay. I hope you're pleased that we've been able to cover in the last 2 lectures the law of sines and the law of cosines and been able to solve triangles now. Given certain pieces of a triangle, we can find the other pieces. These formulas are very, very useful in applications of calculus. They don't form a main theme of a calculus course, but they're often used when you're solving an applied problem. Next lecture, we'll turn to something really quite, I won't say quite different, but it's a new direction. It'll be talking about something called vectors. Vectors play a key role in calculus because they describe motion. Vectors have both magnitude and they have a direction associated with them. This vector going this way will be different than a vector going this way. The difference to keep in mind is speed is something that just measures how fast you're going, like your speedometer on a car. But velocity in mathematics and physics is not only the speed, it's also what direction you're going. So I could be going 50 miles an hour in this direction. That would be a different vector from going 50 miles an hour in this direction. So next time we'll look at vectors and talk about some of their applications. I'll see you then.